Okay, so we'll, as we said, the last topic is dimensional analysis. We'll continue with this. I had given the introduction in the last class. Now, now today we will list out the steps and methodology of using dimensional analysis. And I will simultaneously uh, illustrate with an example. So, maybe I'll divide the whole thing into two parts. So, okay. Step one in any problem will be to list all the dimensional parameters involved, and this will mean both dependent and independent variables, including the ones which are used in the boundary conditions. And as an example here, so on the right hand side, as I said, I will take an example. So suppose if it is given to us that drag force on a cylinder let us say FD depends on the density of the fluid, the velocity with which the cylinder is moving, the diameter of the cylinder, and the viscosity of the fluid. So, this is density, velocity, in some problems, if density per se is not important, then instead of viscosity having the dynamic coefficient, we may have the kinematic coefficient, which is new. So these parameters, now in real life, you will have to determine these parameters. Of course, for a classroom situation, they may be given to you. But you come across a real problem, you see a tower which is there, you want to find how much force is the wind exerting on the tower. And how we use that, I will come to once I finish the process. So there, then you will have to think of these things. It will depend on the height of the tower, the width of the tower, the density of the fluid, density of air which is going, the velocity with which wind is blowing, and then viscosity would be an important factor. And maybe there may be some other factors. Also, you'll realize among these variables, there will be two types, dependent and independent. The independent are the ones which you don't control, or uh, and the dependent variables are what you will be finding out. That is what your aim is, to find these dependent variables. So this was step 1. Step 2 here is we select a set of fundamental or primary dimensions. And the fundamental dimensions which we normally use, for example, mass, length and time, maybe theta if there is temperature, q if there is some electric charge involved. And in this example, again, we use mass, length and time, because the dimensions density depends, is m by l cube, velocity is l by t, so l, m and t. Sometimes people, instead of using mass, may also use force. But then you can't use force, mass, length and time, because force can be, you can make a dimensionless parameter using force, mass, length and time. So then you don't, within these fundamental parameters, you should not be able to make a dimensionless group. So that is the governing principle here. So should not be able to and this is sort of obvious also. The fundamental parameters are chosen that they are independent. So you choose something like mass, length and time, etc. Then step 3 is to list the dimensions of all parameters in terms of primary dimensions chosen in step 2. So our variables here were Fd was the drag force. So how do we choose it? We know it is mass times acceleration. So m times L times t to the power of -2. And the square bracket is used to denote the dimensions. Okay. Which was the other thing? We had Fd, then we had rho. So dimension of rho would be so this is now this mu, you may have your doubts, but these things you can straight away see mu is what mu times dv by dy is stress. So using that you can easily get this. Or if you know the units of mu, it was Pascal seconds, so from there you can get it. And it's useful to remember these. So this is sort of, at least some of these variables, density, viscosity, they will appear in all the fluid mechanics problem. Of course, I can give you a solid mechanics problem which uses dimensional analysis. So there again, you'll have to do the same thing. The method stays the same. Okay. Now, we said set a, just let R be the number of primary dimensions which you have used MLT. Let that number be R. So in this example, R is 3. So next thing after that, we select a set of R dimensional parameters then we select from these total n parameters we had, we will choose R parameters which within themselves contain all the 3 basic parameters, which means our basic parameters are MLT. So when we choose these R parameters, within these 3 parameters, there are 3 in this example, at least one should have M, at least one should have L, and at least one should have T. So this is the basic guidelines. So here the guidelines, there are a couple of guidelines we give. One, the R parameters should have all basic dimensions, and B, within these R parameters, within these R parameters, we should not be able to form a dimensionless group. For example, if I choose length as one of the parameters, then I cannot choose, if there's another area is another example. So I cannot choose area and length as 2 repeating parameters, because area divided by L square will make a dimensionless group. And the third, this thing is, generally we avoid the dependent variable is not chosen as these R parameters so these parameters which we have, we call these R parameters as the repeating parameter. Now let's go to the example. In our example, what was there? Fd was a function of rho v d mu. So which will be the repeating parameters we will choose? Well, one is, as we have decided, number C says the dependent variable should not be chosen. So we will not choose f as a repeating parameter. So we are left with 4, rho, v, d and mu. And we can choose any 3 of these. So in the example, we choose rho, V and D as the repeating parameters. I could have chosen rho, V and mu also. I could have chosen mu, V and D also. Because see, one of these, rho or mu, is needed to get M. V and D do not contain M. See, D we choose because D is a simple parameter. Always try to choose the simple parameters if they are there. So D becomes one obvious choice. Time, velocity, when we look L by T. So time comes in because of velocity. To get in mass, I will either need rho or mu. There is another guideline for choosing these repeating parameters. In some of the problems when you read, it may say F is dependent on, let us say, 10 variables. Then please read the full problem. The part D may say that force is linearly proportional to one of the variables, or it depends on one of the variables as square or cube. So do not choose that second variable also, because that will help you to simplify the analysis. And again, we will see that once we take example. So in addition to not choosing the dependent variable, if a functionality is given between the dependent variable and one of the independent variables, then do not choose that independent variable as a repeating parameter, because that will help you make life easy. You can choose it, still you can work it out, but the reason for that will become obvious in a minute. So for example, here we choose rho VD. And the next, which is straightforward, step 5, we set up dimensional equations combining the parameters selected in step 4 with each of the other parameters to form dimensionless groups. Now this step is sort of an obvious step. Let's say we have chosen rho, V and D as the repeating parameters. So I will look at the first parameter. There are only two left. Which are the two left? F and mu. So I'll look at F and try to combine it with various combinations of rho, V and D to get a dimensionless group. And how do we do this? So here again, let's see, we have F. So what I will do is I will say dimension of F times dimension of rho to the power of A, V to the power of B, if this has to be a dimensionless group, then the dimension of F times, and A, B and C we have to determine by now substituting these things, and let's see how to do it. But you can also do this by inspection. While I am writing this, this is if you come across some new variable for which you do not know anything. But how do we do this by practice? Let's see, what is rho V square? Bernoulli's equation, we know rho V square has dimensions of pressure. So pressure multiplied by area is force. So that means rho V square D square will have dimensions of force. So what will be the dimensionless group? Force divided by rho V square D square. So this is how you get it by inspection. And the more formal method, which I'm now doing this, so let's first do this. Force is equal to ml t to the power of minus 2, mass times acceleration, mass this times rho, rho is equal to m by L cube, velocity is equal to L to the power of b, t to the power of minus b, and d is L to the power of c is equal to L0 m0 t0. So now let's equate. So we get a, sorry, 1 plus a is equal to 0, and then I do L. So this is from M, from L I get 1 minus 3a plus b plus c is equal to 0, and for time minus 2 minus b is equal to 0. So this gives me a is equal to minus 1, b is equal to minus 2, and c will also come out to be 1 minus 3a, so 4 minus 2. So therefore, the we get f, we called it fd times rho to the power minus 1 and this dimensionless group, we call it as a pi group. Since this is 1, I can call it just pi 1 or pi whatever. Okay. Now just here we can also get it by inspection, and my rho v square is pressure, and pressure express the functionality in terms of pi number. So now here what we have is fd divided by rho v square d square is some function of mu by rho vd. Okay. So this is how you just solve these problems. So this is the first step in solving these problems, is to express. Now dimensional analysis will not give you the nature of this function f, whether it is linear, sinusoidal, cubic, or to the power -1, log, exponential, nothing will be told by dimensional analysis. Dimensional analysis will just be able to simplify up to this. But still, here you realize we started from 5 variables and we have now got only in terms of 2. So, this is the basic step in dimensional analysis. Now, this is the first step. Now, I will take another example which will illustrate how you have to be a bit more careful. And this example of the capillarity effect because of surface tension, liquid rises in a narrow tube. If we immerse a narrow tube in a liquid, the liquid rises, and this rise is attributed to surface tension. And here what we have is, if this height h is given to be a function of d, gamma and sigma, where d is the diameter of the tube, gamma is equal to rho g, and sigma is the coefficient of surface tension, which means it is force per unit length. So, if you are to express this as a, we are supposed to do this problem. So, if I express the dimensions h is L, d is L, gamma is rho g, rho is m by L cube times g is L by t square. So, this is m divided by L square t square. And what is surface tension sigma? This is force ml by t square into 1 by L is equal to m by t square. Now the question comes, how many repeating variables do we have? So this was the first step we have done. We expressed everything in terms of the basic dimensions. Now and if we blindly follow what we have said, our basic dimensions are how many? 3. So L, M and T. if we say L, M, T are the basic dimensions and choose 3 repeating variables. Choosing 3 repeating variables is wrong in this problem. Why? If you look at the dimensions, M and T always occur as M by T square. So suppose if M by T square was alpha, then you would have had only L and alpha. That means you should choose 2 repeating variables, not 3. So look at these dimensions, and if you see 2 of them are either occurring in the same way or they form a dimensionless group in all the combinations, then you cannot choose them as 2 different repeating variables. So in a problem like this, you have to choose only 2 repeating variables, not 3. Is that clear? Because M and T square together form M by T square, which could have been just a single variable. Suppose if there was a 4th variable containing M square upon T4. So still you would have chosen only 2 repeating variables, because M square by T4 would be M by T square whole square. Or if there was another thing containing T square upon M, that would have been M by T square to the power minus 1. So you don't choose that, you don't use one more repeating variable because of this. So this example I have taken just to show this. So therefore, since M and T appear in all the variables as M by T square, the same form we choose okay. Is everybody clear with this? So then we choose 2 variables. So the 2 variables we choose, obviously we do not choose H, unless of course if nothing else is available, then we will choose L, because H is what we have to find. H is the dependent variable. So we choose D and we choose one of gamma and sigma. So let us say we choose D and gamma. So then we get pi 1 is equal to H by D and pi 2 is equal to sigma divided by gamma D square. So this pi 2, I'm not doing the detailed calculation. These are new variables, but you can work it out. Either you use the same logic, force divided by length is sigma, and from there then, and gamma is rho g, you have to multiply it by L cube to get force, and so on, and then you can easily get this. Okay. So this is how then this problem. And finally, so the answer here will be H by D is function of some function of sigma upon gamma D square. Now, of course, another student can write H by D is a function of gamma D square upon sigma. That is also correct, because we are not specifying what the function is. So even if you take it as this function or even put a square or cube or whatever, the answer is not wrong because it's just a functionality you are expressing. So now let us quickly see some dimensionless groups which are important in fluid mechanics, and for which what we will do is we'll write everything in terms of some force and then divide the two forces which will give us some dimensionless number. So if you look at inertia force, which actually is not a force, inertia, which is the left hand side of the Navier-Stokes equation, if I write it in terms of force, this is something like mass times acceleration. So this will be equal to the, what we will assume is there is a typical velocity in the flow, there is some length scale, and then if we talk of inertia, then mass becomes important. So mass is rho times L cube times acceleration L by T square. So if we express it in terms of, so velocity and length we will take, and we will take the other variable which is coming from the physical property. Here it is density. So rho v square L square gives us a dimension of a force. If I try to find viscous forces, then the way of getting the dimensions, mu dv by dy, this is dimension of what? What is mu dv by dy? Stress, shear stress is mu dv by dy. So that means I have to multiply it by area. That will give me the dimensions of the viscous force. And this I can then write it as mu dv by dy will be v by L times L square. So the viscous force, so here what I'm trying to do is somewhere assuming v is a velocity in the flow, typical velocity, and L is a length scale. I'm expressing all the different forces as a function of the velocity, a typical velocity and a typical length scale. What is the gravity force? Gravity force is nothing but the weight, which is equal to mg. So this will be equal to, in terms of our variable, in gravity force weight will not come, so rho L cube g. A pressure force due to pressure difference delta P, this will be equal to delta P times A. So I will write it as delta P times L square. The force due to surface tension, this will be sigma times L. So this is obvious. Now this we have not done, but if the flow is compressible, then we have a bulk's modulus, and flow due to compressibility is EV times area. But then what we do is, the reason I'm writing all this is, we take ratio of different forces. And typically, we always use inertia as one of the bases, because inertia gives you mass times acceleration. And that will tell, so suppose I want to find how much important is the viscous force with respect to the moving fluid. I will take a ratio of viscous force to inertia force, or the other way around, and that will give me the magnitude of the viscous force. I take a ratio of gravity force to inertia force. It will tell me how much important is gravity in that flow. I take a ratio of pressure forces to inertia force. That will tell me how much important are pressure with respect to the way the fluid is moving. So I take some of these ratios. So ratio of inertia force to viscous force, this is equal to rho v square L square upon mu v L, and this becomes rho v L upon mu. And this is what is called Reynolds number. Now, some of these, the reason I'm doing this is that the way fluid mechanics evolved, uh, the people who discovered the importance of these forces, the dimensionless groups, were given the names on those scientists. And as I told you before, this scientist, his name is Reynolds. And I don't want an apostrophe after the D. A lot of people write Reynolds number, and that apostrophe is sacrilegious. We cannot. He was Reynolds. He was not Reynolds. So, if you ever write this as that is a big no for me. I don't want to see Reynolds' name. He was a very celebrated scientist. His name should not be spoiled. So, we should not put it with the. So, and what we find is Reynolds number turns out to be one of the most important numbers, dimensionless numbers in fluid mechanics. We will not have time, but actually a more correct or more envisioning way of doing this is we take our Navier-Stokes equations and we non-dimensionalize the equations. That means wherever we have any quantity x, y, z, and if we have whatever quantities, we start non-dimensionalizing all the variables. So for example, x, we will write it as x star is equal to x by L, y star is equal to y by L, and so on. And if we non-dimensionalize the equations, then what we will see is the non-dimensional equations will have some of these important numbers which govern the flow come out automatically in those equations. So that is probably a more illustrative way of getting these importance of these numbers. What I am doing here is just sort of more or less not very insightful, but at least one can see something. If we take a ratio of pressure force to inertia force, this gives us delta P times L square divided by rho V square L square, and this is equal to delta P by rho V square, and this is defined as, we define Euler number as delta P. The half does not make a difference. I think when Euler number was defined, this came in from Bernoulli's equation, because in Bernoulli's equation you have a delta P and there's a half rho V square. So Euler number was defined, and in flows with pressure difference, this becomes importance. Then there is another number called a cavitation number, and this is equal to P minus the vapor pressure divided by half rho V square. Similarly, if we have to see the importance of gravity, gravity becomes important in free surface flows. If the body is fully dipped in the fluid, gravity is not that important. But if we are talking of flow of a ship moving in a body of water, there we have a free surface. And in free surface flows, gravity becomes important. And traditionally, the way this has been done is we look at inertia force divided by gravity. Normally we were dividing inertia, but in this case traditionally this has been done like this. So inertia is equal to rho v square L square and gravity is equal to rho g L cube. So this becomes equal to v square upon gl. And what we have is v divided by square root of gl this is called Frau number. And again, Frau was one of the persons, a basic person who did a lot for finding forces on ships and in flows in open channels. So therefore, this number now, as we see, the ratio of forces gives us v square upon gl. But what we call as Frau number is square root of that ratio. So this square root and all doesn't matter because we are talking of dimensionless groups. And so Frau number, which we say, is v by root gl. And the reason why we put things in numbers is, suppose if we talk of a flow situation where viscosity and gravity are important. So then we will directly say it is Reynolds number and Frau number which are important. And what do we do with that importance is what I am following now. But let me just do a couple of more numbers. Weber number. So this is, if surface tension effects are important, the dimensionless group is called Weber number. And finally, we have Mach number, which comes when compressibility effects are important, and this is given by V by A or V by C, and A or C is the speed of sound in that medium. Now there may be because what happens is, again, see how speed of sound comes is how pressure changes with density is related to the speed of sound. So that is how you may be thinking why speed of sound comes into picture, because that tells you how pressure or how density is changing with pressure. And density changes are what is compressibility. So that is how, and this is equal to, again, you need not bother too much. We have not done about compressibility. And what you can see is this Mach number is really nothing but also equal to rho v square L square upon EV times L square. So this is inertia force divided by compressibility force. So these numbers, therefore, now, but how do we use these numbers and why are these important, and why is dimensional analysis so important for fluid mechanics? And for this, what we realize is we talk of flow similarity. And in flow similarity, what we have is there are two things, a model and a prototype. Prototype is the actual. So as I gave an example, for example, if we wish to find wind force on a tall building. So a new building is being designed. It has a shape like this. So this is the paper design. This is the building. There's wind blowing with velocity v past a building, and we wish to find, let us say, the force on the building, or the we may also wish to find the bending moment at the base of the building, so that we design the building according to that. So this is now what we know is from equations, solving this flow may not be possible. As you have seen, exact solutions are possible only when we have very tailor-made situations. You may either do CFD for this, solve it numerically, make a model of a building. Can we do something experimentally? Now, obviously, making the building, doing the experiment, having this wind, and suppose if it fails, it's too expensive. So what you try to see is, can we make a small model of the building? So the building is what, let's say 40 meters high. We make a small model. Small model means 1 meter high model. We make a model of the building and perform tests on the model. It will be easier to perform tests on the model, very obvious, isn't it? And then that means we calculate the forces and moment on the model. Now, of course, these tests will have to be done in a wind tunnel. Wind tunnel is a closed chamber where you can have wind flowing at different speeds. Now, the question then you ask is, based on the forces of or oblique moments on the model, can we estimate the forces and moments on the prototype? Okay? And this is where, if you now think in terms of what we have done at the beginning of the class today, what we realize is, suppose the situation is like we had in the class, pi 1 is a function of pi 2. So now you have two cases, a model and a prototype. Now if you make pi 2, which was on the right hand side, the same for the model and the prototype, then pi 1 will obviously have to be the same. You can measure pi 1 for the model. So pi 1 for prototype will be the same. So that means you can then estimate the forces by getting the value of pi 1. Do you see that or not? Pi 1 is a function of pi 2. So first thing what you do is you equate pi 2s. So that will give you some parameter for the experiment to be done on the model. And once you equate pi 2s, you do the experiment. So that part you have to do and measure the dependent variable and then measure pi 1. And that pi 1 also has to be the same for the prototype. So this is the methodology which we follow when we do similarity or model prototype simulations. So now, so that means what we are doing here is we are carrying out experiments on the model, and we are trying to gauge the corresponding variables on the prototype. Now, for this, certain conditions have to be met. The first thing is that the two flows have to be geometrically similar. For example, I made the model, I said, which means that the model and prototype have the same shape and are geometrically similar. See, the model need not be smaller than the prototype always. As I told you in the last class, if the prototype is extremely small, then maybe the model is a blown up version. So, for example, I am doing test on a aerofoil. Then the actual aerofoil which is used in a plane, the plane wing size may be very large. I make a model, but then this has to be geometrically similar. So, for example, if I make a ring here, if this point is C, this point is A, and this point is D, this is C prime, A prime, D prime, then what we call is A and A prime अभी जो बहुत लेट कोई आए हैं, आई सॉ समबडी कमिंग राइट नाउ, अटेंडेंस लगवा लो, बाद में जाके परेशान करोगे टीए को. आए तो तुम अटेंडेंस के लिए हो, अगर 9 बजे क्लास में घुस रहे हो तो और तो कोई कारण है नहीं तुम्हारा. So all the corresponding points which are at similar locations, we call them as homologous points on the model and the prototype. And obviously, if these are similar, then AC upon A prime C prime has to be equal to AD upon A prime D prime, etc., etc. All these corresponding points, when I look at the corresponding arc lengths, the ratios have to be equal. So, and the shapes have to be geometrically similar. So, for example, the building which I made, it was narrow at the top. The model which you will make will have the same shape. It has to be geometrically similar. Only then you will get the same results. So, this is one thing. And this ratio we can also call as the scale factor. If the model is 10 times, then all these lengths will have the same ratio 10 or 1 over 10, depending on which is the numerator, which is the denominator. So, this is the first thing. Second thing which one has to ensure is kinematic similarity, that is, velocities at homologous points on the model and prototype are related by a constant scale factor. Obviously, the scale factor need not be the same as the scale factor for length. The velocity at 2 points when I look, and if I look at two other points, then the velocities will be in the same ratio. And the geometric similarity is a necessary condition for kinematic similarity. This is obvious. If the flows are not geometrically similar, obviously we can't even talk of homologous points, etc. And the third thing which we get is if the flow conditions are met, is dynamic similarity, and which is forces at homologous points are related by a constant scale factor. Okay. Now, and geometric and क्या आप सिर्फ अटेंडेंस के लिए आई हैं क्या अभी? This is a but 9:10 you come for the class which is supposed to start at 8 o'clock. And so now as an example, we see the drag force divided by rho v square d square was a function of rho v d upon mu. This we saw in the example, we got this dimensional relationship. So now suppose we have a model and a prototype. So what we calculate the drag force on model to estimate the drag force on prototype. Now, how do we do this? Suppose our model is we start with a prototype is a our prototype is a microsphere. Let's say its diameter is 1 mm. We make a model which is a marble. Let's say diameter is equal to 1 centimeter. Okay. Now this prototype we are thinking of some sort of something in the human body, maybe the dimension is even less. I'm just cooking up an example. So in the prototype will move in blood, the density of which is given as rho b, viscosity is mu b, and it is moving with the velocity vb. Okay. Now the experiment is being carried out in air. See, now you see the simplification. You want to find the force on a particle traveling in blood, and the experiment is being done on a marble or on any sphere moving in air, which is much easier to do. So now, given this, so the first thing what you'll have to do is, if we have to have the same results, what you will do is you will carry out the experiment in air, measure the drag force in air. But for this, first thing what you have to do is rho blood, V blood times diameter of the prototype divided by mu of the blood. This will be equal to rho air, V air, diameter of the model divided by mu of the air. So now here the left hand side is given from the real situation. This is what you want. What is the output? What you will get from here will be, you know the diameter, you know the fluid. So this will give VA, or the velocity with which model should move in air. Okay? The fluids are fixed. They need not be the same. Sometimes they are same also. So from here you will first determine VA. Now given this VA, you carry out the experiment. Now this part is something which has to be done. Carry out the experiment on the model with V sub A and find the drag force on the model. Okay. Now what we have is, our dimensional analysis tells us the drag force divided by rho v square d square is only a function of rho v d upon mu. Now since rho v d upon mu are same for model and prototype, the left hand side should also be the same. So since we will be able to find the drag force on the prototype. Okay? Is this clear? Looks like a very simple thing. But actually this very simple thing can help us solve very complex problems. Of course, you will have to do that experiment. But the experiment is much easier to do on a 1 centimeter sphere in air than to do on a 1 millimeter sphere in blood. Okay? क्या चीज? तो हाँ, क्योंकि because we are doing the flow will depend only on these parameters. Of course, what you are referring to comes to suppose if the flow depends on many more parameters, suppose it also depends on the material density of the, see here, we didn't bother about the density, we only bothered about the shape of the material. If the flow would have also depended on density of the material, then we would have had to keep the material also same. So all these things will come, and that leads to a lot of problems. So what I have presented to you is just a very simple this thing, and that is what I was getting to next, that this flow similarity may not be easy to attain. For example, if see here, we took an example where gravity effect was not important. I'm still forgetting about the material of the sphere, etc. If suppose both gravity and frictional effects were important, then what you would have got would be a function of if gravity effect is also there, you will get one more number, which will eventually boil down to Frau number if you use the proper variables. So now, if this is the case, then you have to match both the Reynolds number and Frau number. Now, Reynolds number is rho VL upon mu, and Frau number is equal to. Now, suppose if the length ratio is already fixed, if you match Frau number, that means the velocity is fixed. So, the only way to match Reynolds number will be to use two different fluids. If you use the same fluid, then it will never match. And then finding a fluid which has that same ratio of rho by mu, which this will tell us may not be possible. So it will not always be easy to find similarity solutions, but still we can get a lot of this thing from similarity solutions. Okay. So suppose if we are able to do this, then we can still, if we are able to match both the numbers, then we can still carry out our similarity analysis and estimate the forces on the prototype. Okay. So I think doing this, okay, so this will not be straightforward. You can always think about this. Now, you can always think of Reynolds number. We wrote it as rho VL upon mu. You can also write it as VL upon nu, where nu is equal to mu upon rho. So sometimes things are given in terms of nu. Nu will be equal to mu upon rho. Now, in tomorrow's class, I will take up examples on dimensional analysis, because this topic will not be covered in the tutorial. Well, it's a simple topic, as you have seen, but tomorrow I will take some problems in the workbook and other things which are, so that you can easily solve these. Now, our exam, this is, ye band kar dijiye recording. Let's just